Here is a combined summary of the 2 pages. The U.S. Space Force's doctrine document, Space Power, highlights the importance of space mobility and logistics as a core competency. In response, there has been growing interest in developing technologies to enable in-space operations via in-space infrastructures, refueling, servicing, assembly, and manufacturing, (ISAM). Space logistics has also become a topic of interest for space agencies, aiming to design sustainable space exploration campaigns. Enabling space mobility and logistics capabilities requires a new approach, differing from conventional astrodynamics. This novel approach necessitates logistics-driven modeling and optimization techniques, coupled with astrodynamics, leading to the emerging field of space logistics modeling and optimization. Space logistics is formally defined as the theory and practice of driving space system design for operability and supportability, and managing the flow of materiel, services, and information throughout a space system lifecycle. Although not a new research topic, the literature on space logistics has existed since the beginning of the space exploration era. The idea of logistics network modeling was applied to human space mission design in the early 2000s. Recently, logistics-driven techniques for probabilistic modeling and inventory control have been applied to satellite servicing in megascale constellations. This paper aims to categorize the state-of-the-art studies in space logistics modeling and optimization in 2 ways: by application questions addressed and by logistics-driven methods used in the studies. The first categorization helps practitioners determine what research is available to support their applications. The second categorization systematically maps the existing literature to each logistics research subfield, enabling researchers to understand the state of the art and identify underexplored and promising future research directions. The paper focuses on 3 major applications in space logistics: in-space servicing, assembly, and manufacturing, (ISAM), for satellites, orbital debris removal, and space-based solar power systems. It maps the state of the art in the literature to each research question, highlighting key concepts, methodologies, and findings in each application area. The research paper discusses the importance of logistics-driven approaches in various applications, including robotic in-space assembly and manufacturing, (ISAM), multi-mission space exploration campaigns, and megascale satellite constellations. For ISAM, key questions revolve around analyzing performance, tactical planning, and strategic architecture of infrastructure elements. In space exploration campaigns, logistics-driven research addresses planning and scheduling missions, designing vehicles and resource infrastructure, and responding to uncertainties. Megascale satellite constellations pose challenges in launching and deploying such large systems, analyzing system performance, and managing a commercial ecosystem. The paper maps recent studies to these key research questions, highlighting the need for technical logistics-driven methods to address these challenges. The research categorizes the state-of-the-art in space logistics by application questions, including ISAM for satellites, multi-mission space exploration campaigns, and megascale satellite constellations. For each application, specific questions are posed regarding performance analysis, tactical planning, strategic architecture, and responses to uncertainties. The study also delves into logistics-driven methods, particularly network flow modeling and optimization for logistics planning and scheduling, probabilistic modeling and queuing theory for performance analysis, and inventory control for resource infrastructure operations management. The challenges of applying terrestrial logistics techniques to space applications are discussed, along with the literature's response to these unique challenges. The network flow modeling approach is highlighted as a primary tool for managing space logistics, drawing analogies with terrestrial operations. The example of network modeling for Earth-Moon-Mars exploration logistics is provided, showcasing the nodes and arcs connecting them to analyze and optimize commodity flow. The goals of such problems include finding optimal vehicle, commodity transportation routing plans and schedules to minimize cost functions. Optimizing and analyzing space logistics missions pose unique challenges that prevent direct application of conventional terrestrial logistics approaches. Orbital mechanics, particularly in high-thrust and low-thrust trajectories, require significant computational effort to generate delta V and TOF, making logistics optimization and trajectory design problems coupled. Additionally, the time dimension is challenging to model due to drastically different flight times and complex time-dependent trajectory performance. The nature of space infrastructure also poses unique challenges, as deployment and assembly phases can be as long as utilization phases, blurring the boundary between deployment and operation. This requires considering infrastructure deployment alongside its operations. Fortunately, many of these challenges have been addressed in 30 years of research in space logistics. Network modeling and optimization are the most well-explored fields, with projects like SpaceNet leveraging network modeling for space mission design. Representative works have focused on network modeling for space logistics missions, including depot location problems for ESOM applications and assignment problems for satellite constellation deployment. From an optimization perspective, various formulations have been proposed, including metaheuristics, mixed-integer linear programming, MILP, formulations, and a two-phase approach to decouple nonlinear trajectory problems from integer linear network problems. Two major types of network formulations for logistics optimization include path and node-arc formulations, with the choice depending on the problem's structure, constraints, and solution method characteristics. Recent studies have developed approximate surrogate models to compute low-thrust, low-energy trajectories effectively, which can be incorporated into MILP optimization. To address time-related challenges, multiple techniques have been developed to model and optimize dynamic network flow, including time-expanded networks and other methods. In the context of space logistics, two methodologies are proposed to analyze and optimize the performance of in-space servicing systems. The first method, M1, utilizes a generalized multi-commodity network flow (GMCNF) model that accounts for resource transformation mechanisms with ISRU and ESOM infrastructures. This approach enables the modeling and optimization of missions involving a wide range of space infrastructure systems such as ISRU and ESOM systems. Combining this with a partially periodic time-expanded network, the deployment of resource infrastructure elements and their operations utilization can be concurrently modeled. The second method, M2, leverages probabilistic modeling and queuing theory to analyze the logistics performance of a space system under uncertainties. This approach draws inspiration from how fire stations or ambulance systems are designed to respond to uncertain demands distributed within a city. A spatial queuing model, or orbital queuing model, is proposed to analyze the service responsiveness of an in-space servicing system. However, developing an orbital queuing model poses several challenges beyond direct applications of M.G.1 models due to factors such as limited resources, a finite number of satellites served by a servicer, and dynamic nature of demand and service rates. These challenges necessitate the development of novel methodologies that can effectively address these complexities. In the context of in-space assembly, manufacturing, and recycling, ESOM, effective modeling of space logistics systems is crucial for optimizing resource allocation and minimizing costs. This paper discusses three methodologies to model space logistics systems. 1. Spatial queuing models. 2. Probabilistic modeling techniques. And 3. Inventory control for resource infrastructure operations management. Spatial queuing models, such as the M.G.1K model, can be used to analyze the system's performance under various scenarios. These models account for the time-varying nature of the demand and the dynamic nature of the lead time, which is influenced by orbital mechanics. By integrating an inventory control technique, this model can significantly reduce computational time compared to simulation models, enabling large-scale trade space exploration and optimization in the early stages of design. Probabilistic modeling techniques, particularly the Markov model, have been employed to analyze the system availability of a constellation and design spare strategies. These models can be applied to spacecraft spare inventory, considering Earth as the manufacturer, spare orbits, depots as warehouses, and customer satellites as retailers. A semi-analytic model for a non-orbit servicing system based on the finite source M.G.1 queuing model has also been developed, demonstrating good agreement with simulation models and reducing computational time. Inventory control for resource infrastructure operations management is another key methodology discussed in the paper. This involves applying inventory management concepts to space logistics applications, including satellite refueling or repairing. The demand for fuels, materials, and spares depends on the phase of the satellite's lifetime and thus can be time-varying. An integrated model between queuing and inventory management is often needed to account for the transportation of the servicer, which is governed by spatial queuing models. The lead time distribution in space logistics applications is also unique due to the dynamic nature of orbital mechanics, making the relative position of the depots and customer satellites vary over time. The paper highlights the challenges in applying inventory management to space logistics, including the need for an integrated model that considers both queuing and inventory management aspects. It also emphasizes the importance of optimizing the system to minimize costs and improve efficiency, particularly in the context of ESOM. The research focuses on the inventory management for satellite replenishment, particularly in space logistics. It addresses the complexity arising from multiple depots and customized satellites, considering orbital mechanics. The study reviews the state-of-the-art in inventory control for space applications, highlighting works on multi-echelon inventory models and optimizing inventory policies under uncertainties. Extensions to basic models include concurrent design of vehicle and infrastructure, and incorporating operational uncertainties. For the latter, stochastic optimization, decision rule-based optimization, and a hierarchical reinforcement learning framework are discussed. These approaches aim to optimize the inventory control strategies, taking into account the unique challenges of space missions, such as launch delays and demand fluctuations. The research emphasizes the need for strategic formulations and solution methods beyond traditional logistics research to address the complexities of space logistics. The summary begins by discussing the rolling horizon approach for ESOM applications to respond to newly obtained demand information over time. It highlights the shift towards incorporating multiple players in space logistics, using game theory to optimize incentives for commercial players. The section also touches on the affordability and commercialization of space missions, emphasizing the need for a more decentralized optimization approach. Moving on, it reviews the literature on space logistics, focusing on the applications and methods used. It presents a table summarizing how each reviewed literature is mapped to the corresponding application area and logistics-driven method. The data is split into 3 time frames to show the most impactful papers in each decade. This is followed by an analysis of open fundamental research questions, such as scalable algorithms for large-scale space logistics network optimization and complex queuing networks for space logistics analysis. The research paper provides an overview of the state-of-the-art for space logistics modeling and optimization. It categorizes recent literature into 2 ways: by application questions addressed and by logistics-driven methods used in the studies. The applications reviewed include ESOM for satellites, multi-mission space exploration campaigns, and megascale satellite constellations. The logistics-driven methods include network flow modeling and optimization for logistics planning and scheduling, probabilistic modeling and queuing theory for logistics performance analysis, and inventory control for resource infrastructure operations management. The paper also discusses several extensions of these basic models that tackled unique challenges in space applications. It highlights the importance of understanding the existing research that can answer application questions and the technical perspective of the literature to identify new underexplored research directions. The author acknowledges the support from the Air Force Office of Scientific Research, AFOSR, and the contributions of several experts in the field. The paper concludes by emphasizing the need for further research in critical yet largely unexplored areas. This research paper discusses the planning and execution of human missions to the Moon and Mars, focusing on space logistics, planetary surface exploration, and the optimization of space mission planning and architecture design. It highlights the importance of spare parts requirements for space missions considering reconfigurability and commonality, as well as the optimal planetary surface routing considering exploration values and synergies. The paper also explores the role of on-orbit servicing in enhancing space systems' flexibility and its implications for satellite design and operation. The study utilizes mathematical methods for space mission planning and architecture design, emphasizing the need for integrated thermal structural design of an orbital propellant depot. It further delves into dynamic modeling and optimization for space logistics using time-expanded networks, which is crucial for efficient resource allocation and scheduling in long-duration space missions. Moreover, the paper addresses the economic case for the retirement of geosynchronous communication satellites via space tugs, and the potential benefits of reusable lunar transportation architectures utilizing orbital propellant depots. It also references various programs and projects, such as the DARPA Robotic Servicing of Geosynchronous Satellites (RSGS) program, Northrop Grumman Space Logistics, and the DARPA Novel Orbital and Moon Manufacturing, Materials, and Mass-Efficient Design (NOM4D) program, showcasing the breadth of ongoing research in this field. The research paper concludes by emphasizing the significance of spare parts requirements, optimal routing strategies, and the importance of on-orbit servicing for future human spaceflight missions. It underscores the need for continued development in these areas to ensure successful and sustainable space exploration. This research paper presents a comprehensive review of the state-of-the-art in in-space logistics and servicing, focusing on the economics, architecture, and operations of various systems. The authors cite numerous studies on in-situ resource utilization, ISRU, for Mars colonization, lunar propellant production, and Mars oxygen ISRU experiments. They also reference several satellite constellations, including NASA's Gateway program, OneWeb, SpaceX's Starlink, Amazon's Project Kuiper, and Iridium and Globalstar Low Earth Orbit (LEO) satellite systems. The paper discusses the application of queuing theory to on-orbit logistics and the impact of in-space additive manufacturing and recycling technologies on on-orbit servicing. Semi-analytical models for designing and analyzing on-orbit servicing architecture are presented, as well as two-phase frameworks for near-optimal multi-target Lambert rendezvous and multi-target rendezvous for active debris removal. The authors also explore versatile on-orbit servicing mission design in geosynchronous Earth orbit, frameworks for modeling and optimizing on-orbit servicing operations under demand uncertainties, and optimal multi-target rendezvous using hybrid propulsion systems. They cite research on the orbital facility location problem for satellite constellation servicing depots and the future of asset management for human space exploration, including supply classification and integrated databases. Logistics information systems for human space exploration are discussed, including emerging technologies and a modeling framework for interplanetary supply chains. The paper references SpaceNet version 1.3, a user's guide for space logistics analysis, and matrix modeling methods for spaceflight campaign logistics analysis. Finally, the authors touch on interplanetary trajectory analysis and logistical considerations for human Mars exploration, highlighting the complexities and challenges of in-space logistics and servicing. Overall, this research provides a thorough review of the current state of in-space logistics and servicing, emphasizing the need for continued research and development in this critical area. Here is a combined summary of pages 23 and 24 of the research paper. The authors present a comprehensive review of various research studies and methodologies related to space logistics, mission planning, and spacecraft design. The references cited cover a range of topics, including matrix methods for optimal manifesting of multi-node space exploration systems, comparative usability studies of space logistics analysis tools, and space logistics modeling and simulation analysis using SpaceNet. Several studies focus on the development of mathematical models for interplanetary logistics, including a generalized multi-commodity network flow model for the Earth-Moon-Mars logistics system and a campaign-level dynamic network modeling framework for spaceflight logistics. Other research explores the optimization of in-space supply chain design using high-thrust and low-thrust propulsion technologies, as well as the development of event-driven network models for space mission optimization. The authors also highlight studies on integrated transportation system design for space exploration logistics, multi-fidelity space mission planning and infrastructure design frameworks, and multidisciplinary design optimization approaches to integrated space mission planning and spacecraft design. Furthermore, the references discuss flexibility management for space logistics via decision rules, hierarchical reinforcement learning frameworks for stochastic spaceflight campaign design, and federated simulation and gaming frameworks for decentralized space-based resource economies. Additionally, the authors cite studies on space architecture design for commercial suitability, including a case study in situ resource utilization systems, and a space exploration architecture and design framework for commercialization. The review also covers research on staged deployment of communication satellite constellations in low Earth orbit and optimization of satellite constellation deployment strategies considering uncertain areas of interest. Overall, the authors provide a comprehensive overview of the state-of-the-art in space logistics, mission planning, and spacecraft design, highlighting the diverse range of methodologies and approaches being explored in this field. The provided pages present a comprehensive literature review on satellite constellation replenishment and optimization, as well as game-theoretic approaches to modeling competition between satellite constellations. The authors cite various studies on satellite constellation design, optimization, and replenishment strategies, including works by Disson and Weiss, 1966, Kelly and Dasuki, 2004, and DeWeck et al., 2008. The review highlights the importance of optimal replenishment policies, citing studies by Jung and Ren, 2009, and Jakob et al., 2019. It also touches on the regional constellation reconfiguration problem, referencing Lee and Ho, 2023. The authors further discuss interactive simulation games and multi-stakeholder approaches to assessing federated satellite systems, drawing from works by Grogan et al., 2014, 2015, 2016. The review also explores game-theoretic models of competition between satellite constellations, citing Gazzetti et al., 2022, and Qureshi et al., 2022, 2023. These studies develop frameworks for modeling economic competition between Pleo constellations, using techniques from operations research and logistics management, as seen in Larson and O'Donnell, 1984, and Simchi-Levi et al., 2014. The authors also reference finite source queuing systems, as discussed in Strick, 2001. The literature review sets the stage for the authors' proposed approach to satellite constellation replenishment and competition modeling, which will likely involve integrating insights from these various studies to develop a novel framework. The review highlights the complexity and interdisciplinary nature of satellite constellation optimization, emphasizing the need for a comprehensive and game-theoretic approach to address the challenges of replenishment and competition in this domain.